short set of videos, we're going to be looking at root finding. So when in the real world would you expect to find a root finding problem? So the example I give here is the example of artillery. So in the image on the right hand side of the slide there, we have a 155mm howitzer. It's firing a shell. You can actually see the shell exiting the muzzle here. I don't know whether that's been photoshopped in afterwards or not. What we hope to do is the shell follows some trajectory and lands across here at the target. How do we find the mathematical problem, however, for this root finding problem? Often in this unit, and this will come up a few times, is that you'll be asked to derive the equations that define that. So how do you do that? Well, let's have a look at this very simple example. The things that we know, hopefully, are the position of the target, in other words, the vector that describes where the target is, and let's just say that the origin of our system is here at the howitzer. So we've got a vector that goes from here across to there, that's RT, and the position of the shell. That's something that changes as a function of time, but it also changes based on the angle of inclination of the barrel. So our root finding problem becomes, when does the vector RT equal the vector RS? Remember here that RS is actually a function of two different variables, t and theta. So in other words, if we just write that as a single function, when does the distance between these 2 points, d of t and theta, which equals this thing here, when does that equal 0? That's how we mathematically write the root finding problem here. Now obviously, in different cases it's going to be trickier to do that. But you need to begin to think about, what do I know, and how can I turn that into some kind of mathematical function? So there's a few fundamentals that we need to remind ourselves on for root finding. The first thing is, when have we actually found the root? Okay, so if we have some function represented by this black curve here, for a root to be exact, we need to know that y, which is equal to the function value at the root, f of xr, that has to be identically 0. In other words, that green point there. If the function value at x of r is identically equal to 0, then we have found the root exactly. In practice, in computations, this is not possible to achieve because of round-off error, because of finite arithmetic, and a whole bunch of different reasons. So we're going to have to accept an approximation. And so what we say is, if the absolute value of the function at some value of x is less than epsilon, in other words, where epsilon is a small tolerance, and we have we can choose that to be whatever we like it to be, if f of x is less than epsilon, then we're going to say we've found the root. So in other words, at this value x minus across here, that function value there is equal to negative epsilon, but the absolute value is less than epsilon. And on the right hand side we'll have an x plus, where the function value is equal to epsilon. So anything inside that blue region there, between x minus and x plus, we're going to classify that as a root, because the function value, or the absolute value of the function, is going to be less than the tolerance epsilon that we have specified. And usually what will happen is, when we're going through our numerical algorithm, we will choose some value in here. We don't know what it's going to be beforehand, and it's the first guess within that region that's going to give us the root. So we hope that this distance between x plus and x minus is small. The other thing we need to be aware of is that there's different types of roots. And there's two basic types. There are single roots and there are multiple roots. In order to describe what the difference is, and again you should have learnt this in 1060, let's consider the polynomial f of x is equal to x times x minus 1 squared times x minus 2 times x minus 3. And if we plot that function up, it looks like that curve there. The single roots occur at x is equal to 0, x is equal to 2, and x is equal to 3. And they are associated with each of these terms in the polynomial. And they're called single roots because the power of each of these terms is 1. And the function, of course, crosses the axis at each of these points. So it's positive on one side and negative on the other. In contrast to this, the root at x is equal to 1, which stems from the term x minus 1 squared, is what's known as a double root. And it's called a double root because the power here is 2. Okay, you can actually have higher order roots. And the multiplicity of a root, third order, fourth order, etc., is determined by the Taylor series expansion about that particular root. Now, I'm not going to get you to do anything with this, but you need to be aware there are single roots and higher order roots, not just double, they can be triple, quadruple, etc. So, root finding, at least for simple one-dimensional root finding, there are two basic classes of methods that we'll look at in subsequent videos. The first are known as bracketed methods, and the second are known as open methods. As I said, you learnt this in Eng 1060, although I am going to briefly review it here. You are expected really to know this already.